So I would like to introduce you here my three TAs, Mr. Mahmoud Nasser, Mohita Chowdhury, and Ambarish Ravi. They are going to help me in this course. They happen to be my students, and one of them is my former students who kindly accepted to support us in this course, Mahmoud Nasser. And the three of them are very well versed in the field of the course, which is on computational intelligence, machine learning. So they are working on, one of them has finished his thesis in the field of implementation of machine learning for e-health system. Mohita and Ambarish are working on their master thesis utilizing the fields of computational intelligence and machine learning as well for two application areas. Check here. So this is the course logistics. So this is a summary, very brief summary of what the prerequisite for the course, the workloads, the textbook. So the textbook, as I mentioned to you, are not going to be mandatory. If you would like to buy them, if you would like to rent them, if you would like to purchase them, I mean, that's up to you. But I will post some of the material from the textbook, I mean, the authorized material that is on the websites. The lecture slides are going to encompass most of the techniques, most of the material that you need to read for this course. And of course, I will post as well some material from articles throughout the term. So that's the course logistic in general. And I will be very happy to receive feedback from you. Please feel free to email me as much as you want, and I will be happy to respond to you within one day when you are sending the email. Most probably I will respond to you within a few hours. So feel free to email me if you have any feedback or you would like to convey something about the material that I teach in this course. I would be happy to get any more feedback. You can also email my TAs. I mean, they are very happy to help you out, and they are happy to receive your comments and convey them to me. I mean, if you would like to do it through them. So this course, again, is about soft computing, intelligent systems, computational intelligence. A lot of people call them different names. And we call them computational intelligence. That's the formal title of the course. I call them also soft computing. I mean, both have been used, often in the field of artificial intelligence. As we are going to see throughout these slides, computational intelligence is a set of tools that help users to tackle a particular problem utilizing data sets or labeled data or information knowledge that people captured from experience about a particular process, how to utilize them, how to utilize the prior experience in order for you to create models that are going to provide you with a powerful predictive type of capability in the future when you don't have access to this particular type of data. So the origin of modern computing and neural network and AI, dates back to the 1940s. And here I'm tackling mostly the aspect of the machine learning components and neural networks. So I'm not tackling the fuzzy logic component here, which is going to be the main focus of our course in this particular set of lectures for this term. So you can see from the top left, the modern computing started with von Neumann, who has developed the von Neumann machine, which has the main system that we are utilizing up to this day in our laptop, in our desktop, even in our supercomputer system, the system composed of a main memory, arithmetic logic unit, program control units, and an output that you can see visualize in terms of data or visualize it in terms of images. Then came Rosenblatt perceptron in the 1950s and the 1960s, who has who's basically the father of what we call neural network systems. He has developed the first successful perceptron system, which is completely different architecture from the von Neumann computer, and it tries to provide computation based not on the central processing unit of the system or the main memory of the system, but rather the system tries to utilize a set of computational components, how to cooperate with each other, and how to provide a particular type of output for the system. And this has been used especially for classification purposes in the early days of the perceptron. And then came the time of John McCarthy, 1950 to 1970s. And he's one of the first people who have developed the first algorithm for artificial intelligence, which we regard today as the main growth of intelligent systems nowadays. So the time of AI and John McCarthy, I mean, was spanning between 1950 and 1970. As you can see, it has overlapped for a certain period of time with the Rosenblatt perceptron system. And the area of AI, as proposed by John McCarthy in the 50s, 60s, and the 70s, hasn't taken off as many people have wanted. And people try to go back to the connectionist modeling of Rosenblatt and develop even more powerful type of technologies based on connectionist modeling. And this has given birth to the early days of what we call it nowadays deep learning, which is what most people are saying now. It's what we call AI. So what we call application utilizing AI is no other than deep learning type of technologies. And this has been developed, I mean, in the early 1990s and in the early 2000s. Schmidhuber was one of the pioneers of this type of technologies in the field of deep learning. There is also Jeff Hinton, who has developed some of the technologies related to this. I mean, he has developed some of the major connectionist modeling in the form of multi-layer perceptron, but he has also contributed to the progress and the studies of deep learning, especially in the late 90s and in the early 2000s up to 2010, when the area of deep learning has exploded. We will talk about the history later on when we tackle deep learning type of system. So this is, I mean, an historical progress of what has been done. I haven't put here the progress that was noted in the field of fuzzy logic systems, which was fathered, if you would like to call it, or initiated or created by the father of fuzzy logic systems, Lotfi Zada, who's one of the pioneers of computational intelligence systems. So when we look at variety of challenges that have been noted in for several years in the 50s, in the 60s and 70s, 80s, even the 90s, there were a lot of issues, I mean, on replicating the main capabilities of a human in the field of understanding speech by a machine, how to detect and recognize faces and objects, how to navigate in cluttered and previously unseen environments. So these were challenges that people have seen when they tried to create algorithms or create machines that would like to mimic the human in this particular type of fields. Although there are a lot of theories at the time in the field of pattern recognition, in the field of the early machine learning, if you call it, and the AI expert system in the 70s, the 80s, and the 90s, but people were not able to create powerful and useful machines for this particular purpose. So these were problems that have been, I mean, a major challenge for companies, for people to utilize this particular system. And some of these particular problems were only resolved with very high level of accuracy, very high level of precision and reliability only in the past 5 to 10 years that we start to have almost a machine that is perfectly understanding speech, for a machine that detects and recognizes faces with high level of accuracy, how to navigate robots or a machine or a car within previously unseen environment, and still they can operate reliably. So these type of problems have remained only, have only been solved in the past several years. This is a particular big problem because we were not able to decipher this problem, how to implement pattern recognition algorithm to solve these particular problems. There were two major aspects for the challenges that were presented. First of all, the computational systems that were available were not powerful enough to store and to archive the data and to retrieve it in real time to make use of powerful pattern recognition type of models or artificial intelligence models. And the second part, we did not have access to hugely, to large patterns, large set of patterns or data that are labeled. And we are going to speak about the labeling of data later on when we are going to tackle machine learning aspects. So these two particular type of challenges, remained up to 10 years ago, up to 12 years ago, when we have, cheaply available large amount of data sets and powerful type of computational machines that we were able to solve this particular problem. So the algorithms were there in the 80s, in the 90s, they have been developed, but people were not able to utilize them. So today, we see major breakthroughs, similar to the cat brain simulation system called Synapse at IBM. There are so many type of problems that have been resolved over the past few years. Google's DeepMind, you hear almost on a weekly or on a monthly basis, some of the major discoveries by DeepMind or Google Research Project or Facebook or Microsoft or Amazon. And most of these type of discoveries, most of these type of achievements in the area of artificial intelligence mostly are using tools of deep learning systems, whether supervised, unsupervised, or reinforced learning type of tools, using deep structures and using deep learning type of technologies. IBM Watson question and answer system also, which was developed over the past few years, has become really very, very powerful system. It's like a human encyclopedia, but with so many type of domains, and it keeps improving as we speak. These are type of systems. IBM is not the only one that is working on this particular technologies. There are a lot of companies around the world that are working on this particular fields. I'm not mentioning these type of companies to advertise them or to promote them, but simply because scientists and research people in these companies, Amazon, Google, Facebook, Microsoft, are developing type of technologies that are being used to support their products, but also to help the community at large to utilize their big data analytics library and also their data sets. I remember that when I was teaching courses in AI and computational intelligence 15, 20 years ago, one of the major problems is not teaching the algorithm themselves, but the problem was to have access to data sets that we can utilize, that we can work on, and we can mine knowledge from them. Nowadays, many type of data sets are available, and we are going to show you through the assignments how to access some of these type of data sets at publicly available repositories. So when we speak about intelligent system, in this particular course, we are speaking about artificial entities that are involving a mix of software, hardware systems, devices. They are distributed type of modules integrated under one single umbrella and they are behaving in a certain way to achieve capabilities of perception, reasoning, learning, and making inferences from incomplete information. And some of the autonomous cars nowadays, some of these autonomous drones that you are seeing are simply artificial intelligent systems that are using these type of capabilities for perception, reasoning, learning, and making inferences. The only difference from these type of systems that are developed nowadays and the system before is that nowadays we are able to integrate all these powerful capabilities, sensory perception, reasoning, learning, making inferences within a microchip. So we can build all these type of perception systems and the capabilities for intelligent system in a very small microchip that we can integrate with very small devices. And that's why we call this type of systems intelligent systems. They used to be very huge systems, which we call them intelligent systems, but nowadays they could be hidden into a small microchip, and they have very powerful capability for transmission information, for perception, for reasoning. So some of the intelligent systems that we are familiar with, includes license plate recognition in part of highways, fingerprint recognition, which has been developed, several years ago, utilizing tools of pattern recognition, the conventional pattern recognition. But nowadays, you can have very, very small computers in your pocket or very small cell phone, and hidden in it is software capable to, connect with the clouds, and it can give you whether a person who's, who's suspected of something or whatever. You don't need to go to the huge repository or to the main office of the FBI or to the police station to do this type of thing. So you can do it, imminently for fingerprint recognition, for keeping the law, or for some other type of application, or even for authentication. We authenticate every day now, on our cell phone using fingerprint recognition system, and we utilize certain software that is within our own cell phones. Cancer detection, and this is, an area that has been prospering over the past few years. It's not only cancer detection now, it's also COVID detection, utilizing X-rays, and it has been developed over the past year since the events of COVID, the devastating events of COVID that has hampered, the whole world. So we are utilizing artificial intelligence tools, and that will provide you with certain type of reading on this particular systems, including some of the publication and the work that I have done with some of my students in these fields. Autonomous navigation is also another area of intelligent systems. So you have a microcomputer in your car that is able to navigate autonomously and in a cluttered environment, in a cluttered traffic, and it can navigate, very, very, very safely. Of course, these systems are far from perfect. Even the human are not perfect themselves, but this system have gone from somehow accurate to very accurate. And today, certain type of systems are hugely accurate systems within a particular type of environment for detection, for classification, or for clustering capabilities. The main characteristics of an intelligent system is basically a feature that is going to generate an output for you based on certain inputs. The input could be an image, it could be a signal from speech, it could be, it could be a set of data that have a certain type of features, and the system is going to provide you an output based on what the system has learned or what the system has seen in previous experiments. And the output could be a signal, it could be an image itself, or it could be a decision, that is based on the inputs of the particular system. It is commonly accepted that an intelligent system possesses one or more of the following characteristics and capabilities. So these are the generic capabilities. So any type of systems that has two or more of these capabilities, we call them intelligent systems. So this is the consensus that we have among the people who are working in this particular field of intelligent system, AI. A system that has 2 or more of these capabilities could be called an intelligent system. And these capabilities include sensory perception, pattern recognition, learning and knowledge acquisition, inference from complete information, inference from qualitative or approximate information, adaptability, inductive reasoning. So any 2 type of capabilities for a particular system are going to qualify the system as intelligent. Of course, systems, change from one system to another, and it's up to what people have done in the past, what people have integrated in the past that you call the system intelligence. If a system has sensory perception, if the system has reasoning, but the system has provided bad decisions over and over and over again, then you cannot call the system intelligent system. So the system has to be itself, has certain type of these capabilities, but the output has been over time improving over the experiences and improving as long as we provide the system with additional amount of data, with additional amount of knowledge. Example of intelligent systems, of course, the human body is an intelligent system because we have the perception, we have the reasoning, and we have the action, the decision that we take for that particular system. A company, has an input variable that is in the form of information, how much the company has sold a particular quarter, how much the company has delivered to customers in a reliable type of manners. So all of these type of things are type of information. For a power plant, fuel rate system, the consumption of a power plant for the system, if the fuel rate is decreasing for a particular type of engine, and the output of the system in terms of generating electricity or generating certain type of outcome is increasing and is improving, then you say that this power plant is becoming powerful and more intelligent. The automobile system, the wheel movement, the steering wheel movement is an input variable for an automobile system. We know nowadays that there are cars that are fully autonomous, but for cars that are semi-autonomous, where you have the steering wheel movements that is working in an environment that is snowy environments or heavy rain environments or whatever, then the car might help you take a decision when to change a lane, when you have to stop before a certain number of meters before the next car in a particular type of situation. So all of these are type of input variable that a system could look at as the input for the intelligent system. The output variable could be a muscle contraction after our brain has provided us with instruction what type of muscle you have to move in order to move your body to achieve a particular type of task. The company has to take some decision if the product is not very well delivered in time, so then the decision has to be improved, and a company has to improve its overall behavior, or dynamics of how to work and how to get a particular input and deliver a good output for that particular system. The robot system, the joint motion, how to be less chattery, how they can access a particular type of objects without damaging that particular object. So all of these type of systems are possible outputs for quote-unquote intelligent system. And in between the input and the outputs, there is the brain of that particular system, and there is what we call the machine intelligence for a particular system. So if we look at this intelligent machine here, which we call it, intelligent machine, so you can see that there are some sensory capabilities, in the system. There are the sensory perception, which is, the higher level of intelligence for the system. This particular information is filtered out from the sensor, of course, from the process to the sensor to the sensory perception, and goes to the brain. And the brain is going to assess this particular information and is going to deliver certain type of decision. And this type of decision is going to be addressed to the controller of the system, if the system is a dynamic model, it's not a software particular model, and the controller is going to later on impact the actuator. The actuator are going to be the muscle of the process. So the controller, the machine intelligence is the brain. The controller is going to be the information that goes from the brain to the actuator in very moderate and in measured type of way to reach the actuator. The actuator is going to be the muscle of the machine process that is going to take the signal, actuate it, and amplify it in order for it to reach the machine of the system. So it's exactly like the human type of structure. So we have the sensory layer of the human body. We have 5 sensory layers, as we know. And then we have the sensory perception, the filter type of signals that go through whole sets of channels to reach our brain, which is the human engine, the machine, the intelligent engine. And then it's going to be delivered, is going to deliver a decision that is going to reach the actuator, the muscles of the human body, to retrieve an object or to push an object or to do a particular type of action. So it's very, very similar to how human behave in this particular aspect. And as you can see, there is the communication interface. So the communication interface is no other than part of the architecture of this intelligent machine system. So this is an artificial interface where, at every instant of time, data is being exchanged through this pipeline of data that is circulating between the various type of components. And we can see that the components are, between the sensory systems, the sensory perception, and the communication interface. The information goes to the machine intelligence, the brain of the system, then the controller, the actuators, and all of it goes through the communication interface. So this is a particular type of architecture that we design for an intelligent machine system. So this is another example of a manufacturing type of system where you have the natural intelligence of the human that are doing the research, development, innovation to create this type of system and to improve them. So there is the artificial intelligence component, there is the control system, there is the sensory components. This is the process, the manufacturing type of process. We have the various type of environments, we have the various type of machines here, the material that comes to these processing plants, the information knowledge that is going to be going through the supervisory control, which is a component of the overall intelligence of the system. And then the system is going to provide you with a product, with services, and of course, ultimately, if the company is successful, with revenues. So these are very, very simple example of what we mean by an intelligent machine. Let me go very briefly here on knowledge-based systems. So we have database systems and we have also knowledge-based systems, okay? And the knowledge-based system is going to be one of the components of the course that we are going to look at later on in the course, which is in the area of fuzzy logic system. But here it's very brief definition of what we mean by knowledge-based system. So a knowledge-based system is able to make perceptions and new inferences or decision using its reasoning mechanism. So here we are talking about experiences that we have learned from the past. We create certain set of rules, and these type of rules are going to dictate the behavior of the system from that particular experience. And we select only the successful type of experience from which we have inferred how the system is going to manage the inferencing mechanism within this particular type of knowledge-based systems. So we are going to see here, we are going to look at rule inferencing later on, the notion of fuzziness, the notion of perception, the notion of uncertainties. We are going to look at them later on in the later part of the course. So the decision-making process, of course, the inferencing engine. So there is a whole architecture for this type of system. So we have the knowledge-based rule of productions, which is going to communicate with the reasoning mechanism, which is the brain of what we call the inference engine. We retrieve, we get information as we speak from a certain type of database. Database provide us with the contexts with the situation of that particular system at a particular time. So this is going to be like the input for your particular system. It goes to the reasoning mechanism, and then it's going to go to the human interface, which is going to improve the knowledge-based system throughout experience, how to improve the knowledge base, how to improve the rules or production. This is especially for expert systems and for fuzzy inference systems that we are going to see later on in the course. So I'm not going to go over the details for representation of knowledge, I mean, using knowledge-based systems, because we are going to look at them, but mostly the processing of the knowledge that we are going to tackle later on might include logic, might include semantic networks, frame, production systems, fuzzy logic systems. In this course, I'm going to possibly look at some aspects of logic and semantic networks, but mostly is going to be based on fuzzy inferencing mechanism. And that is going to be the later parts of the course, because as I mentioned to you, I am going to emphasize in this course mostly machine learning systems, connectionist modeling, classification, prediction, and deep learning systems, and how to utilize these type of capabilities. And later on, I will go to fuzzy logic systems. So I'm going to skip this part, which is the crisp logic, which is basically the discrete mathematics that we have seen. I'm sure many of you have taken course in discrete mathematics in the past. So I'm going to skip this part and possibly speak about knowledge processing here, how to tackle the knowledge, how to improve the knowledge engine of a particular system. I mean, so there are three major characteristics: simplifying the knowledge base, substituting into the knowledge base the new information, so basically updating the inferencing mechanism as we receive some additional information from a particular type of processes, and applying an appropriate rule of inference. So we are going to see this within the context of fuzzy logic systems. So let me now talk about what we are going to see mostly in this course. I mean, what is the notion of soft computing, computational intelligence? We have spoken so far about intelligent systems in general, what AI has been doing over the past few years. So now I'm going to get a little bit more focused on what we are going to see in this course and how to define soft computing, computational intelligence. So soft computing or computational intelligence is an important branch of study in the area of intelligent and knowledge-based systems. So this is a set of computational tools that are allowing us to make intelligent decisions, mimicking the behavior of a human, mimicking the decision-making process of a human, using either data sets, labeled data, classification techniques, machine learning techniques, or utilizing knowledge-based representation such as fuzzy inferencing mechanism. So these type of approaches, these type of techniques provides what is known as computational intelligent tools. And that's what we are going to study in this course. Of course, computational intelligent tools also includes another components, which are evolutionary type of computing. So if we look here, the computational intelligence tools, so we have the neural networks, we have fuzzy logic systems, but we have other type of approaches, evolutionary algorithms such as genetic algorithms, rough set theory. So these are other type of theoretical framework that people have developed under the umbrella of computational intelligence. In this course, we are going to tackle only the first two components, and mostly the first component, neural network, machine learning. I'm going to do most of the emphasis. The 2/3 of the course are going to be based on machine learning and neural network for this course. Fuzzy logic is going to be 1/3 or even less of the course because the technology has evolved, and I would like to basically teach you some of the most recent tools in the field of computational intelligence. I usually teach evolutionary algorithms in the graduate component of the course alongside with neural network fuzzy logic. I'm not going to teach it in this course. I might allude to it during the study of the gradient descent algorithms for optimization of neural network systems. So I will speak about it a little bit in order for you to know the power of these type of algorithms and how people could utilize them to improve the capability of optimization of the neural network structure. Rough set theory is outside the scope of this course, so this is also an area that have been people have been including. I mean, in the area of the computational intelligence, people also have included uncertainty measurements and the probabilistic theory as part of computational intelligence. So I don't want to confuse things, but I would stick with these four approaches in the field of computational intelligence. And for the sake of this course, we are going to focus only on the first two, which are related to the neural network and fuzzy logic system. So this is the description of what I just mentioned. So fuzzy logic system, probability theory, neural networks, genetic algorithms or evolutionary algorithms are cooperatively used in soft computing. So people are not using one single tool of them. So for very complex process, and I'm going to show you later on in the course how to integrate some of these computational intelligence technique to come up with the most powerful type of intelligence system that we can build. Of course, our system could be built using neural network systems or powerful machine learning type of tool, but we are going to see as well that in certain type of cases where the process is extremely complex, where the process requires a certain type of perception, knowledge representation, then it is better to include, machine learning tools with fuzzy logic tools and genetic algorithms to cooperatively work together to provide and to develop an intelligent system. So that is going to be in the later part of the course when I am speaking, summarizing the course content in the last lecture or the last two lectures, and how to benefit from these type of tools in the future. So fuzzy logic system, so very, very brief definition here. Fuzzy logic system is useful in representing human knowledge in a specific domain or application and reasoning with that knowledge to make useful inferences or actions. So fuzzy logic system, different from the binary or bivalent logic systems, discrete mathematics that you have seen in your undergraduate studies, in the fact that it represents the human knowledge when we are representing the information. So the information is not represented to processes as true or false, but the information could be presented as somehow true, somehow false, very true, very false. So we are going to describe these type of human knowledge representation and map it to this particular type of technology, which we call it fuzzy logic system. So we will speak about this later on in the course. So I'm not going to go over the detail, but I comment here, fuzzy logic system, allows for realistic extension of binary crisp logic. So it makes the crisp logic, the discrete mathematics representation, the binary logic systems more expansive in terms of extent of the utilization. And it is very useful in real world situation where the description of a particular model is not described fully by true or false, but by through certain type of partial truth or partial type of falseness, if we would like to call it that way. So, for instance, an example of a fuzzy rule would be if the speed of a car is slow and the target is far, then moderately increase the power. So the target here, it means the car in front of you. So if the speed is slow, so you have enough distance and the target is far away, then moderately increase the power for the accelerator of your system. So here we are not speaking about true or false, the speed is high or low, or the speed is 90 kilometers or 100 kilometers. We are speaking the speed is slow. And we are going to see how to represent these particular type of what we call hedges, in this type of fuzzy rule information. Very powerful type of technology that people have been utilizing for the past 30 years, 25 years, 30 years, with exceptional type of accuracy and power. So let me talk about the neural network, which is going to be one of our major representation for our major modules in this course. So neural networks are, I mean, very, very brief description here, massively connected networks of computational neurons, and represents parallel distributed processing structure. So if we go back to the second or third slide that I shared with you today, you remember the perceptron, the early perceptron model. So the early perceptron model is the parent of this type of neural network. Neural networks have been evolving over the past 50, 60 years, but they have seen the hugest increase over the past 6 to 8 years when we have developed the fields of deep learning systems and its utilization in nowadays applications in the field of computer vision, natural language understanding, translation systems, decision making, stock market predictions. All of these have been developed. I mean, very powerful tools have been developed over the past few years, and artificial neural networks that have started seeing the day in the late 40s, early 50s, now have come to fruition in a big, big way to humanity. And what we are seeing nowadays, I mean, the major growth in the field of machine learning, in the field of deep learning, has taken roots in these very early discoveries of Rosenblatt in the 1950s or McCullough in the late 40s. So the key characteristic of neural networks, as we are going to see it later, is their ability to approximate arbitrarily nonlinear function for function prediction, or to provide us with an accurate classification when the outcome of the neural network is discrete. Basically, you have certain type of categories to which you classify a category in one of the multi-type of possibilities that the system is providing you. So this is the perceptron, I mean, the early basic components. This is the Rosenblatt perceptron. We are going to see it later on when we are going to talk about the structure of neural network in a few lectures from now. Probabilistic reasoning is another area of computational intelligence. We are not going to see it during this course, although we are going to talk about fuzzy logic reasoning. We are going also to touch a little bit on probabilistic reasoning, but we are not going to go into the details of probabilistic reasoning and how to impart a classifier or to impart a predictor or to create a predictor based on probabilistic reasoning. We are going to see, though, that most of the neural network output is based on stochastic type of functionality that is hidden within this neural network. And I will explain this later on when we are going to tackle the main engine of machine learning systems and the main engine of neural network systems. Uncertainty versus fuzziness. This is also a concept that I'm going to showcase you when we are going to tackle fuzzy logic system. Uncertainty is different from fuzziness. I will explain to you some of these type of differences later, but uncertainty is mostly statistical inexactness due to random future event. Fuzzy system is not statistical inexactness. It is a firm type of decision based on a partial type of labeling of that particular representation of the system. So probabilistic systems nowadays have also cooperated with fuzzy logic system in a complementary manner in a certain type of application. And if we have time later on in the course, I will give you some example on this particular aspects. So this, I mean, table showcase some of the fuzziness versus uncertainty for a particular system. So the advantages, disadvantages. So where we have in the advantages component here, where we have incomplete information which can be handled for fuzzy logic system. Uncertainty is useful in situation having random influences with known probability distribution. So whenever you have probability density distribution for a particular system, probability density function that represents a distribution, then you have quite a bit of knowledge for which you can represent a priori type of a posteriori type of event for that particular system. And although we are not going to use Bayesian inferencing in this course, but I might speak a little bit about it later on when we are going to compare fuzziness versus probability system. So fuzziness systems are particularly useful in representing and processing human-oriented knowledge. So when we speak human, describe a particular type of thing, I mean, we usually represent it into less than exact type of information. We know what we mean, but when we represent it, we don't speak that this is true or false. So we speak about a certain type of fuzziness. The weather is somehow cold today. So this is an example. The weather is somehow cold. So it means that compared with the day past, so the weather is colder today. So we understand this type of inferencing. So this is not uncertainty. So this is what we call fuzziness. So this approximate reasoning, we are going to look at it and we are going to study it. And I will give you the major aspects of how to represent linguistic knowledge that is qualitative utilizing fuzzy systems. Of course, fuzziness and uncertainty or probabilistic representation, each one of them has its own disadvantages, and depending on the situation at hand that you are able to represent this particular type of system. So, of course, fuzziness, when the environment is not very well known and you have seen it for only the first time, so the inferencing for fuzziness may introduce a degree of inaccuracy. And that degree of inaccuracy could be learned in the future and could impart some level of exactness for the system as we proceed with a particular type of experience. Fuzziness also needs prior knowledge and experience of the problem in generating the knowledge base. As we are going to see as well in fuzzy sets theory, we require prior knowledge. We require prior experience, how a particular process has worked in the past. We have to translate the working of that particular process into a set of inferencing rule. So we are going to see the complexity in developing that, but we are going also to see some methods on how to circumvent these particular aspects. So approximation, which we are going to see it as part of soft computing, is related to intelligence, the human being, I mean, how to deal with the approximation for the purpose of comparison, pattern recognition, reasoning, and decision making is a manifestation of intelligence. How with non-complete type of data, how with an approximate representation of a certain type of system, and we are providing still an accurate representation of the model, that is intelligence. That's how human, we call them intelligent because they have these type of capabilities. So I'm going to impart these approximation capabilities, whether for machine learning type of systems, from which we are going to have, repositories that are not complete in the form of the data, and yet the system, when it learns, when it captures more experience, the system is able to provide us very accurate type of information about the class or about the predictive outcome of that particular system. So we are going to see all these type of capabilities, but approximation is a soft concept, and that's why we call it soft computing. How to be able to deal with the approximation while we represent a system that is powerful, that is able to do reasoning with only a partial knowledge of the information. Of course, the partial knowledge of the information has to encapsulate within it powerful capabilities and powerful information from which the system is going to do some inferencing, or the system is going to do reasoning or decision making. So we are going to see the threshold beyond which the system is not going to be intelligent. The system is not going to be powerful, even though it is an approximator. So there are approximation challenges for where we say that the system has a good judgment or bad judgment, or is doing good classification. And to do that, we are going to talk about performance measure of this particular type of system. And this is going to be also a component that we are going to see in this course. So let me end here with these type of concepts that are in the field of approximation. And approximation softness mostly is going to be dealing with fuzzy logic systems and subjective probability later on, and we are going to integrate as well the machine learning components for the system later on as part of an approximation system. So we see on the left-hand side the concepts. and where we have the ambiguity, vagueness, generality, imprecision, uncertainty, fuzziness, belief, plausibility. So for each one of these type of concepts, we have a certain type of property. So the fuzziness is different than imprecision, as you can see here. The fuzziness is different than vagueness. So when we say that a system is fuzzy, it doesn't mean that the system is vague. So as you can see, the property, the condition is not precisely defined. In fuzzy system, there is membership of the condition that is not crisply defined, but we know the membership function. We know the boundary of the condition is not crisp, but we know about it. In the vague system, we don't know anything about it. And as you can see on the left, on the right-hand side, you can see some of the examples for all these particular type of concept. So we are going to study many of these type of concepts later on, but let me see, let me go. So here I would like to conclude by saying that significant advances have been made in machine implementation of characteristics of intelligence, such as sensory perception, pattern recognition, knowledge acquisition, learning, approximate reasoning, and there is a lot type of advances to be made in the next several years. A lot of studies, a lot of innovations are being made on a daily basis in several research centers around the world, in the field of machine learning, in the field of fuzzy logic systems, in the fields of Bayesian networks, in the field of inductive reasoning. So all of these compose what we call it significant advances, and not one particular tool can be utilized for all type of applications. So during this course, I'm going to teach you when to use machine learning, when to use supervised learning, when to use unsupervised learning, when to use reinforcement learning, although we are not going to go through reinforcement learning in details. I will introduce it to you, but we are not going to go through it in details. When do we use deep learning systems? Do we have to utilize always deep learning systems? Or sometimes for simple system, we need only very simple network to provide us a very, very powerful classifier? When do we use fuzzy logic systems? So I'm going to respond to all these type of questions when we go through the course. Every time that I introduce to you a module of the course, I'm going to explain to you what is the requirements, what is the need to achieve or to utilize a particular type of tools that we are going to develop in this particular systems. So that's what I wanted to talk to you today. I mean, this is an introductory material, and it will be posted today alongside with the lecture that I have recorded here. And the first part of the lecture, the first 5 minutes, have not been recorded, but I mean the remainder of the lecture is here, and I will talk next time, starting next time, about the need for machine learning system, the powerful requirements for machine learning systems, and we'll start on the various components of this particular course by divulgating the various modules that we are going to discuss during this course. I will be happy to hear your comments, I mean, by emails. I might utilize also the Piazza system to respond to your need and to respond to some of your queries, but also feel free to email me, to email my students about any question you might have about the course, about the various components of the course, and I will be happy to help you and support you during this term. So thank you very much for attending the lecture today. I would like to conclude, I mean, at this particular stage. I mean, we haven't gone through the full time, so this is an introductory lecture, but I wanted to share with you the major type of components that we are going to see during this course. And I would like to have this course as interactive as possible, although it might not be very, very, very easy, but my TAs, and with the help, I mean, with many help from you and from your feedback, I will be happy to respond to your queries. I might respond to one or two of your questions if you would like. I mean, we still have a few minutes left. If you have some questions or anything about the material of the course, please feel free to unmute yourself and ask your question. Okay, so if you don't have any questions, so feel free to email me. I will be happy to respond to you. And thank you very much for attending today's lecture. And I will be posting the lecture slides within the next few hours. I will also post the links for our recorded lecture today. And again, feel free to email me or any of my TAs about the requirements of the course, about anything that you think about the course. I will be happy to respond to it. Thank you very much, and I'll see you next Friday.